now we'll start integer. This is one important topic in classical algebra, and this topic is important in B.Sc and IIT joint entrance examination. And also we'll solve some important problem, especially for Calcutta University students. Okay, now we'll continue this lecture. So here the first recall the set of all integer, the set of all integers is denoted by z and is defined by the z equals to 0 plus minus 1 plus minus 2 plus minus 3 plus minus 4 and so on. If we draw a number line, that means real number line, and we can represent the integers in that way: 0, 1, 2, 3, 4, 5 and so on. Similarly, on the other side, minus 1, minus 2, minus 3, minus 4 and so on. And also we have seen the set of all integers, set of all positive integers. Here the note the set of all positive integers, that is a proper subset of Z, proper subset of Z is identified with the set of natural number, with the set n. Now the question is, what is n? Where n is basically the set of all natural numbers, set of all natural numbers. Now the set of all natural numbers means 1, the number which are used for counting. So 1, 2, 3, 4, 5 and so on. And this is also considered as Z plus. Also, the set of all negative integers, this is denoted by Z minus, and this is minus 1, minus 2, minus 3 and so on. So our note 3 here, note 3, this is note 2. So we can represent Z as set of all negative integers union 0 union set of all positive integers. So that means we can represent is Z minus union 0. Set of all positive integers is basically n. That's why from here we can write set of natural number is a proper subset of set of integer. Now whatever we will discuss in number theory, that means in integer. So here our number is basically coming from integer, and we will discuss different properties and algorithm. So before that, we will try to recall one important statement. This is called the well ordering principle. Well ordering principle. Well ordering principle. Sometimes this question is asked in graduation course. What is the state well ordering principle? So well ordering principle is if it is a set of natural number, then every non-empty subset of n, every non-empty subset of n, subset of the natural number n has a least element. So as for example, say if I say is equals to 5, 1, 7, 200, 401, 2023, 2024, 107 and 560, like this. So this is basically subset of N, and you will see the least element of S. The least element of S here is basically 1. So that means every subset of just to verify with this example, but okay, you can take any subset of N and you can observe the least element of the set. So this is, that means we can think about well order. So well order means we can, they have list element is 1, then we will find out the next list element, that will be 5, then next list element, that will be 7. In that way we can order it well, in a well manner. So well ordering principle says us exactly the same thing. Now we'll move to another important, we call here, this is called the division algorithm. This you can consider as a theorem. So here the theorem is division algorithm, and that we are basically, this is well known to us from class 1, class 2 or class 3. So algorithm, now the question is, what is the statement of the division algorithm? Say when you have two integer a and b, and if you divide the integer a by b, so there will be a quotient and there will be a remainder. That format we know. From that we can state it easily. The given integers a and b, given integers a and b with b greater than 0, then there exist unique integers. So quotient and remainder will be unique. So that's why unique integers q and r belongs to z, such that unique integer such that the relation a equals to, here the relation is a equals to bq plus r, and where 0 less than equals to or less than b, such that a equals to bq plus r, where 0 less than r less than equals to r less than b. So this is basically our division algorithm. Okay, but we can prove the division algorithm, and that proof is also important. So here proof is basically self in exercise, and you can see any kind of book where integer is written, especially you can see in the Mapa book, there is proved how the division algorithm is basically holds. That proof is already there. So now we will continue another important concept here. This concept is basically divisibility concept. So next recall, saying a definition of divisibility. Divisibility. So what we said here now by division algorithm, if we divide a by b, there exists unique integer q and r. Here the relation is a equals to bq plus r, where 0 less than equals to or less than. Now just to think about if r equals to 0, this special case. So in that case, a equals to bq, and we can say b divides a. B divides a. That means a is divisible by b. Okay. So an integer is said to be divisible by an integer. An integer a is said to be divisible by another integer b, but b is non-zero, if there exists k or there exists q belongs to z, such that a equals to bq. And we can write this symbol and we denote it In that case, we denote it B divides A. Just you draw a vertical line, B divides A. So here the note, if you see x and y both are integer, let x and y both are integer with y not equals to 0, then y divides x, that implies x equals to some yk for some k belongs to z, and obviously k is for some k belongs to z. So this note is very important. So now we come to some important questions. The question is, if A divides B and B divides C, then what we have to prove? Then prove that A divides C. Okay, then prove that A divides C. Now question is how to prove this kind of question. So what is exactly given? What is exactly given? So it is given that A divides B and B divides C. What we have to prove? So we have to prove that A divides C. That we have to prove. So now start from A divides B, and that implies B equals to some AK1 for some Q1 belongs to Z. So that we have taken with the help of divisibility. And B divides C, that implies C equals to BK2 for some K2 belongs to Z. Now we will show A divides C, that means we will show C equals to some A into some integer. And from that case, we can write A divides C. So what is exactly C here? So here C means BK2. So that is 1 and this is 2. So this is basically by 2. Now in position of B put the value of B AK1. So AK1 K2, this is by 1. That we can write AK1 K2. That means A divides C as K1 into K2 is integer. Why they are integer? As K1 K2 both belongs to Z, that means both are integer, and product of two integer is integer. So that means what we have proved? A divides C. So this proof is simple. Now there is another important recall. This recall is important and helpful to solve the problems. The recall is if A divides B and A divides C, then we can say A divides Bx plus Cy where xy belongs to Z, where x comma y belongs to Z. Okay. If A divides B and A divides C, then A must divide Bx plus Cy. So we can prove it easily, and this holds for any integer xy belongs to Z. So what is given? A divides B. From that we can write B equals to A k1 for some integer k1 belongs to Z. Again A divides C, that implies C equals to A k2 for some k2 belongs to Z. So now start from Bx plus Cy. So B means A k1 x and C means A k2 y. Okay, and from that we just take common A. We take common A, so that will be k1x plus k2y, and that implies A divides Bx plus Cy where x comma y belongs to Z. Okay, so in fact the note is for all xy belongs to z, A divides bx plus cy if A divides b and A divides c both. So that also true for xy, any xy belongs to z. Now we'll come to next important question. The question is, prove that for any m consecutive integers, the question is, prove that this question is very very important. The product of m consecutive integers, the product of m consecutive integers is divisible by m, okay, where m is basically a natural number. That means product of two consecutive integers is divisible by 2, product of three consecutive integers is divisible by 3. That we have to prove. So how to prove this kind of problem? So first we will take m consecutive integers, then we will take the product, and after that we will think about it is divisible by m or not. So let the m consecutive integers be m consecutive integers b. Say I have taken integers c plus 1, c plus 2 up to c plus m minus 1. So this is basically our m consecutive integers. Now with the help of division algorithm, we can write, if we divide the integer c by m, okay, there will be some quotient, there will be some remainder. So that means c equals to mq plus r, where 0 less than equals to r less than m. So what we write here, by division algorithm, there exist integers q and r belongs to z such that c equals to mq plus r, where 0 less than equals to r less than m. Now the thing is, so here the remainder is basically either 0 or 1 up to m minus 1. So these are the possibilities. So start from when r equals to 0. If r equals to 0, in that case c equals to mq. Just put r equals to 0 here, and in that case m must be divide c. But when r equals to 1, what will happen? Then c, you will take this integer c plus m minus 1. C plus m minus 1, that will be, what is the value of c? C will be mq plus 1. So mq plus 1 plus m minus 1. So that means mq plus m, and that we can write m into q plus 1. In that case also m divides c plus m minus 1. Similarly, when we'll take r equals to 2, when r equals to 2, then we take the previous number c plus m minus 2, we just put the value of c here, value of r here in this expression. In that case c will be mq plus 2. So mq plus 2 plus m minus 2, that will be m into again q plus 1, and that implies m divides c plus m minus 2. In that way, we are continuing till when r equals to m minus 1. So the last possibility. In that case, c plus 1, just to put here the value of r m minus 1. So c will be m cube plus m minus 1 plus 1. Again it will be m into q plus 1, and that implies m divides c plus 1. So that means in any case m divides either c or c plus m minus 1 or c plus m minus 2, or m divides c plus 1, whatever the remainder. The remainder may be 0. So therefore whatever integer r may be, therefore what we conclude, whatever integer m r may be, it may be 0, it may be 1, it may be 2, it may be m minus 1, m divides one of the integers either c or c plus 1 or c plus m minus 1. So that means it implies m divides the product c into c plus 1, c plus 2, c plus m minus 1. That means we can generalize it, the product of m consecutive integers is always divisible by m. So hence our problem is proved. Now we have the important note in that by using this result we can say 2 divides n into n plus 1. Why? Because n and n plus 1 are two consecutive integers, it must be divisible by 2. Similarly 3 divides n into n plus 1 into n plus 2, because n plus 1, n plus 2 are 3 consecutive integers, and this holds for any n belongs to natural number. Okay, and in that case, this is your exercise. You can solve the 6 divides n into n plus 1 into n plus 2. You can take any integer also, no problem, for all n belongs to z. Okay, and from that we can prove, because since we'll see that GCD of 2 and 3, this is 1. So that means we can say here the product of 3 consecutive integers is always divisible by 6. Always divisible by 6. Okay. Now we come to the next important question. The question is question number 2. This question is very, very important. Use division algorithm. To prove that the square of an odd integer is of the form 8k plus 1. What is k? Where k is an integer. So now the thing is how to solve this kind of question with the help of division algorithm. So now the odd integer is always of the form. Okay. So if we take any integer, say any integer q. So and if we apply division algorithm, what we can write? So by division algorithm, algorithm, every integer, say your integer is n, if we divide by 4, so it may be, that is a quotient and remainder. So the r, what is the possibility of r here? 0 less than equals to or less than 4. So r may be 0, 1, 2 and 3. So every integer upon division by 4, leaves one of the remainder, either the remainder may be 0 or 1 or 2 or 3. That we can see with the help of division algorithm. So therefore, any integer is of the form is one of the form. It may be 4q if the remainder is 0. It may be 4q plus 1 if the remainder is 1. It will be 4q plus 2 if the remainder is 2. Or it may be 4q plus 3. So these are the possibility. If we divide an integer n by a number 4, so depending on the remainder, we can say what should be the form of the integer. So it may be 4q or 4q plus 1 or 4q plus 2 or 4q plus 3. And the question is, what is q? So where q belongs to z. Now among these, which will be the odd? So 4q plus 1 and 4q plus 3, that will be the odd integer, and 4q and 4q plus 2 both are even. So this integer and this integer will be odd. So obviously here we can write, therefore odd integer are of the form 4q plus 1, or we can say 4q plus 3. If we take 4q plus 1, now we'll check the square of an odd integer is of the form 8k plus 1 or not. So now we take the form 4q plus 1 and we are doing squaring it. So we are squaring it, and that will be 16q square plus 8q plus 1. So that we can write 8 into 2q square plus q plus 1. So obviously this is of the form 8k plus 1. What is k here? Where k is here 2q square plus k, and this is also an integer. Okay. Now if you take 4q plus 3 square, that will be again 16q square plus 24q plus 9. That we can write, you can take the common 8 into 2q square plus 3q plus 1 plus 1. This is 9. So that means again it is of the form, just consider this as a k, so 8k plus 1. So this is of the form 8k plus 1, where here k equals to 2q square plus 3q plus 1, that is also belongs to integer. So that means what we have proved, the square of an odd integer is of the form 8k plus 1. So thus, or hence we can conclude, hence the square of an odd integer is of the form 8k plus 1, where k belongs to z. Now we come to next important concept. This is basically GCD. Recall, GCD, greatest common divisor, greatest common divisor. Okay, and you will see the terminology. The terminology first is the divisor, then common divisor, and after that we will decide it is greatest or not. So sometimes here the notation is GCD of AB. Okay, greatest common divisor AB. So we need to find out what will be the GCD of, but there is a restriction. Okay, the restriction is when we will find GCD, greatest common divisor of two integer. So in that case, A, B are not both 0. That means where a square plus b square is non-zero. And that is at least one of them is a non-zero integer. Okay. So this is very, very important. So that means we can't find out GCD of 0, 0. This is not possible. But okay, this is possible, GCD of A0 or GCD of 0B, but where A is non-zero here and B is non-zero. So when we will find out the GCD of two numbers, so among these two integers, at least one of them must be non-zero. So now we will come to the definition. How to define, what should be the definition of the greatest common divisor? Let A comma B belongs to Z be such that a square plus b square is non-zero. That means at least one of them is non-zero. Then we can define GCD of AB. Then the greatest common divisor of A and B is denoted by GCD AB and is defined by GCD of AB equals to some D, where D satisfies following condition. Now the question is, what are the conditions? D must divides A and D divides B. That means D will be the common divisor. Okay, that is D is a common divisor of A and B both. And second, so this is the common divisor part. And second part, if there is any common divisor, if C divides A and C divides B, then it must happen, because this is the greatest, so C must divide D. Okay, so GCD of AB will say D, but D satisfies these two conditions. Then D is called the GCD of AB. And there is another important note: GCD of any two integer AB, that will be equals to GCD of minus A comma B. That is also equals to GCD of A comma minus B. This is also equals to GCD of minus A minus B. What is AB? Where A comma B both are integer and A square plus B square are non-zero. From that condition, we can conclude GCD of AB always non-negative, greater than equals to 0. Whatever the GCD of AB is always non-negative. Okay. Now we come to the important questions. The question is question number 3. The question is show that GCD of a comma a plus 2, this is equals to 1 or 2 for every integer a. For every integer a. How to prove GCD of a comma a plus 2 will be 1 or 2? So now we come to the solution. We assume that let D equals to GCD of a comma a plus 2. Then according to the definition of the greatest common divisor, D will be the common divisor also. So D must divides a and D must divides a plus 2. We know the fact if a divides b and a divides c, from that we can write a divides bx plus cy for all xy belongs to z. That means we can write d divides ax plus a plus 2y for all xy belongs to z. Okay, that we can say. And this relation holds for all integer x, y, z. So we just take x equals to minus 1 and y equals to 1. X equals to minus 1, y equals to 1. So obviously the above result holds. So therefore from star, what we can write, D divides a into minus 1 plus a plus 2 into 1. And that is exactly 2. So that means D divides 2. So there is a possibility D equals to 1 or 2. So that's why D is our GCD. So we can conclude here GCD of a comma a plus 2, that will be D. D is either 1 or 2 for every integer a. And there is another important recall. The recall is if k is positive integer, then GCD of KKB, that will be k into GCD of AB. What is AB? Where a and b both are integer and one of them is non-zero. Now we come to the next important concept. This is relatively prime or co-prime. When two integers are called relatively prime or co-prime, so let a comma b belongs to z, then a b are called a comma b are called relatively prime to each other, or co-prime if and only if GCD of AB equals to 1. So if GCD of AB equals to 1, then it will be relatively co-prime. So here the example, you will see GCD of 4, 9. 4 and 9 both are not prime, but GCD of 4 and 9 is 1. So you can say 4 and 9, that pair they are co-prime to each other. Again, you can take any two prime numbers, say 5 and 7. This is also 1. So any two distinct prime must be co-prime to each other. So 5 and 7 are also co-prime to each other. So co-prime does not mean it will be both the A and B will be prime. No. So if you calculate GCD of two number and it is 1, then this two number is also called the co-prime. Now we come to next important concept. The concept is here you can consider it as a theorem. The theorem is for the co-prime case or A and B are prime to each other, you can say A and B are prime to each other. So co-prime or relatively prime can also written as the language may be prime to each other. Prime to each other. Okay. So here 4 and 9 are prime to each other, still they are not prime. So here you have important theorem. This theorem is important for exam. Let A and B be integers not both 0, otherwise we can't find out the GCD. Then AB are prime to each other, then A and B are prime to each other, if and only if there exist integers u and v belongs to Z such that AU plus BV equals to 1. Okay, so that is integer u and v such that AU plus BV equals to 1, and we have to prove this theorem. So what is exactly given? We need to prove the both sides. We need to prove here. First we consider A and B are prime to each other. From that case we will prove there exists integer u and v such that AU plus BV equals to 1, that side, and then we will prove the converse part. Okay, so first we assume that. So how to prove? Let A and B be prime to each other. And from that case we can prove that there exists u and v belongs to Z such that AU plus BV equals to 1. So A and B are prime to each other. That means then what we can write according to the definition of relatively prime. So GCD of AB equals to 1. And GCD of AB equals to 1. And from that case we can directly write there exists U and V belongs to Z such that AU plus BV equals to 1. Or you can write 1 equals to AU plus BV. Why we can write? Since we know this, recall, if D equals to GCD of AB, that implies D divides A and D divides B. So 1 equals to GCD of AB, that implies 1 divides A and 1 divides B. And here we can write D divides AX plus BY for all XY belongs to Z. So we can write 1 divides AU plus BV for all UV belongs to Z. Okay, and for all UV, but there is some particular UV. For that AX U plus BV equals to 1, that will be whole. So now conversely we will assume that let there exists integer U comma V belongs to Z such that AU plus BV equals to 1. What we have to prove? We have to prove A and B are prime to each other. That means they are relatively prime to each other. So that means we have to prove GCD of AB equals to 1. Okay. So now I am considering let D equals to GCD of AB. If we prove D equals to 1, and from that case we can write GCD of AB equals to 1. So how to prove? So D GCD of AB, so that means D must divides A and D must divides B. And that implies D must divides AU plus BB. That implies D divides 1. Why 1? Because it is given AU plus BB, this is 1. And since D is a positive, D divides 1 and D is greater than equals to 0, so D must be 1. That means GCD of AB equals to 1 and A and B are prime to each other. So our proof is done. So we conclude that A and B are prime to each other if and only if there exists U comma V belongs to Z such that AU plus BV this is equals to 1. Now here we can prove there is another important theorem, and this theorem is important. What is the theorem? The theorem is if A divides BC and GCD of AB equals to 1, then A divides C. How to prove this theorem? So here proof is what is given. It is given A divides BC and second information is GCD of AB equals to 1. What we have to prove? We have to prove that A divides C. So since GCD of AB equals to 1, what exactly mean? So there exists integer U comma V belongs to Z such that AU plus BB equals to 1. Just I am using the previous theorem. And from that, we can write ACU plus BCV equals to C for any integer C. Okay. Now since A must divide AC because there is a factor there and A also divide BC. This is given. This part is given. So that implies A must divides ACU plus BCV. Okay, because U and V both are integer. And ACU BCV, by using star, we can write A divides C. So what we have proved here, we proved here A divides C. Proof is done. Now we come to the next important theorem. Next important theorem, theorem number 3. What the theorem 3 says? If A divides C and B divides C with GCD of AB equals to 1, then we can say AB divides C. How to prove this theorem? How to prove it? What is given? The given information are A divides C and B divides C. And second information is GCD of A comma B equals to 1. So what we have to prove? We have to prove that AB divides C. Okay, so since A divides C, and that implies C equals to A K1 for some K1 belongs to Z. Again, B divides C, that implies C equals to B K2 for some K2 belongs to Z. Okay, so that means here, therefore, C equals to A K1 equals to B K2. Now, since GCD of AB equals to 1, and that implies there exists integer u comma v belongs to Z such that AU plus BV, this is equals to 1. Okay. So therefore, you just multiple C on the both sides. Therefore, we can write C equals to ACU plus BCV. Now, what is the value of C here? What is the value of C here? The value of C, that will put BK2. So this is 1 and this is 2. So A BK2U plus B, again we put the value of C here. So this we have put here by 2. Now by 1, C equals to AK1, we will put here AK1. So again by 2 and 1. So if we take the common AB, it will be K2U plus K1V. And that implies AB divides C. Since K2U plus K1V, this is also an integer. Okay. So what we have proved, we proved AB divides C, and hence our proof is complete. Now we'll do next theorem, theorem 4. If A is prime to B, if A is prime to B and A is prime to C, is prime to C, then A is prime to B.C. Then A is prime to B.C. Prime to the product of B and C. So how to prove? What is given? Given A is prime to B. So A is prime to B, that means GCD of AB equals to 1. Is prime to B. Now A is prime to C. That means it is also given GCD of AC equals to 1. What we have to prove? We have to prove that A is prime to BC. That is, we have to prove that GCD of A comma BC, this is equals to 1. If we prove it, our proof will be done. So now I'll start from GCD of AB equals to 1. Now GCD is prime to B, GCD of AB equals to 1. That implies AU plus BB equals to 1 for some U comma V belongs to Z. In GCD of AC equals to 1, that implies AM plus CN equals to 1 for some M comma N belongs to Z. By using the first theorem, theorem 1. So that we can represent is 1, that we can represent is 2. Now from 1, we just multiple C on the both CN on the both sides. So it will be AC UN plus BC UN, that will be CN. Okay. Just we multiple by multiple by Cn on the both sides. On the both sides. Now what is the value of Cn? Cn is 1 minus am. 1 minus am. This is by 2. Okay. So what we can write here, that implies a into m plus cun plus bc into vn. This is v. Vn, this is equals to 1. Okay. And from that we can write GCD of a comma bc equals to 1. Why? Since m plus cun, this is integer and vn is also integer. So by the help of first theorem, we can write GCD of a comma bc equals to 1. And here our proof is done. So the theorem is proved. So thank you so much.